Welcome to the course on error control coding and introduction to linear block codes. In this lecture, we are going to talk about some of the applications of linear block codes. So, we will first start with a brief historical timeline of how coding theory has progressed over years. Then we will start with some basic examples. We start off with ISBN number and bookland barcode. Then we will talk about universal product code and European article number. Then we will talk about some of the applications of error control coding in practice. So, we will start off with applications in compact disk, and then we will talk about applications in satellite communication as well as deep space explorations. And finally, we will conclude with applications in wireless communications. So, what is an ISBN number? An ISBN number is a 9-digit code with a 10-digit which is a check digit. So, it is a 10-digit number, you have a 9-digit code plus 1 bit which is a check bit. So, how is this check bit calculated? This check bit is calculated as follows. It uses a weighted modulus 11 arithmetic. So, let us denote the 9 bits of ISBN number by A1, A2, A3 and A9. Then the 10th bit is calculated as follows. So, A1 plus 2 times A2 plus 3 times A3 plus 4 times A4 up to 9 times A9 modulus 11 will give us the 10th bit. So, the 10th bit is actually a check bit. An ISBN is typically a 10-digit number where the first group identifies the country, region where the book is published, the second group identifies the publisher, and third group identifies the specific book, and finally the last bit is actually a check bit. So, let us take an example. Let us take this book. This is one of our reference book that we are using, The Theory of Error Correcting Codes by McWilliams and Sloan. So, if we look at the ISBN number for this book, the ISBN number for this book is 0444851 933. Okay. So, let us check whether, so this is the first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, seventh bit, eighth bit, and this is the ninth bit, and this is our check bit. Okay. So, let us check whether this is correct or not. So, how is the check bit calculated? It is A1. So, A1 in this case is 0, A2 times A2 that is 4, 3 times A3 that is 4, 4 times A4 which is again 4 plus 5 times A5, 6 times A6, 7 times A7, 8 times A8 and 9 times A9. Okay. And this comes out to be 102. Now, 102 modulus 11 is, so 11 9s are 99. So, it will be 3 modulo 11. So, this 102 modulus 11 is going to be 3, and that is precisely our check bit is. Okay. Now, the interesting part about these ISBN numbers are that they can detect transposition error. So, what is a transposition error? So, let us say when you are reading this ISBN number with a barcode reader, the most common mistake that happens is the adjacent bits are read wrongly. So, for example, this is 044485193. If it is read like 4044851933, that means these two bits are changed. This is transposition error. Then this particular code can detect such errors. We can verify this. Let us say this is the number which has been read by the barcode reader. We try to find out the check bit in this case. So, this would be, the difference would be, here it is, these two things will be changed because these two bits got. So, it will be 4 plus 2 times 0, and that would be 98. So, this will be 98 mod 11, and what is 98 mod 11? 11 8s are 88, so that is 10. So, that would be x. Note that this check bit is not matching with the check bit calculated this way. So, you can see this particular ISBN code can detect transposition error. The correct number was 04448511933, and these two bits got interchanged, transposition error happened, and you can see using this ISBN number we are able to detect such errors. Okay. Now, by 2007 all these ISBN numbers were replaced by this 13-digit Bookland barcode number. And what are these Bookland barcode numbers? So, a Bookland barcode number starts with 978 and then is followed by 9 digits of ISBN number, and the 13th bit is a checksum which is calculated in this particular way. Okay. This is how we are computing the 13th bit, which is the checksum bit. Now, let us look at an example. So, let us consider our book, this error control coding by Lynn Costello, and what is its Bookland barcode number? That is given by 9788131734407. So, this is the 13 digit number which is given by, which is the ISBN number, 13 digit Bookland barcode number of this textbook that we are using. Now, so this is my A1, this is my A2, this is my A3, this is my A4, A5, this is A6, A7, A8, A9, this is A10, this is A11, this is A12, and this is A13. So, let us look at whether we are getting the same check bit as predicted by this. So, so you can see here what we are doing is all odd digit numbers we are adding them up, right, and all even numbers we are adding them up and multiplying them by 3. So, this would be then 9 plus, let me first take all the odd bit numbers. So, odd bit numbers are these, the ones I am marking by, these are my odd locations, right. So, this is 9 plus 8 plus 1 plus 1 plus 3 plus 4 plus 7 plus 3 times the even numbers. Even numbers are this 7, 8, 3, 7, 4, 0. So, this is 7 plus 8 plus 3 plus 7 plus 4 plus 0. Okay. And this comes out to be 120 mod 10, which is 0. So, you can see from this example that this check bit is correct, because A13 plus this should be 0 mod 10. So, this is an example of a bookline barcode, and all the books now have these 13 digit ISBN number. Now, once they will get exhausted with this 978 number, they will start numbers with 979. Now, next application that we are going to talk about is this universal product code. So, this was basically a standardization of all barcodes, which was first used in 1973. So, there are two versions of it. One is this 12 digit UPC version A, and the other one is this 8 bit UPC version E. So, a 12 digit UPC version consists of 12 digits. The first digit from the left is of UPC type, next 5 digits are manufactured code, the next 5 digits are actually the project code, which are assigned by the manufacturer, and the final digit is the check bit. So, that is what we are going to use for error detection. So, how is this check bit computed? So, this check bit is computed as follows. All digits in the odd positions are summed up. So, you have this UPC number, which is like A1, A2, A3, A4 up to A12. Then what you are going to do is you are going to add up all the odd numbers in the odd location, that is A1, A3, A5, like that, and multiply the sum by 3. So, you are going to multiply the sum of the odd numbers in the odd location by 3, and to that you are going to add all the digits in the even position. So, it will be 3 times A1 plus A2, A3 plus A5 and plus A2, A4, A6, like that. So, you are going to add the number. So, essentially you are weighing the numbers, multiplying by 3, 1, 3, 1, like that, and you are going to add them all up and subtract the sum that you get from the next highest multiple of 10. So, what I am saying is, so you have this 3 times A1 plus A3 plus A5 plus A7 plus A11 plus you have this A2 plus A4, you have these, when you add them all up, plus your 12 bit number, this is your 10, 12, that should add up to 0 modulo 10. Okay. So, the odd bit numbers are multiplied by 3, even bit numbers are just added up. If you add those 11 bits, then the 12th bit, which is the check bit, should be such that sum of this weighted sum should be 0 modulo 10, and that is your UPC code. So, the sum that you should get should be 0 modulo 10, sum of all the 12 bit numbers. So, 3 times A1 plus A2 plus 3 times A3 plus A4 up to 3 times A11 plus A12 should be 0 modulo 10 in case of UPC 12 bit UPC code. Now, a superset of this UPC code, 12 bit UPC code, is this 13 bit European article number. So, what is this 13 bit European article number? So, it has 4 parts. So, first is system code, which is first 2 or 3 bits, which identifies the country where the product has been manufactured. Then you have manufacturer code, which is 4 to 6 bits, and then you have the product code which consists of 5 bits, and finally you have one check bit, and this check bit is computed modulo 10, where the weights in the checksum calculation alternate between 1 and 3. Now what do I mean by that? So you have this 13 bit number A1, A2, A13. So what you are going to do is, these bits in the odd location you multiply by 1, and bits in the even location you multiply by 3, and the modulo sum of that should add up to 0 mod 10. So let us look at an example to illustrate that. Okay, let us look at an example to illustrate that. So I have this Britannia bonbon biscuit, right, and what is this European article number for this? So European article number for this is 890163139190. So this is my 13 bit, you can see 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. This is a 13 bit European article number. Now let us see whether this checksum bit is correct. So what do we need to do? We need to add odd bits, and we need to add the even bits in the even location, and multiply them by 3. So let us first mark the bits in the odd location. This is 0, 3, 3, 1, 0. Okay. And what are the bits in the even location? That is marked with this blue pen. Okay. So let us add up. So again, the check bit is computed modulo 10, where weights in the checksum calculation alternate between 1 and 3. So what do I mean by that? So every odd bit I multiply by 1, and every even bit bits in the even location I multiply by 3. So let me first add up the numbers in the odd location. So that is 8 plus 0 plus 0 plus 3 plus 3 plus 1 plus 0. And this will be multiplied by 1 plus 3 times numbers in the even location. That is 9 plus 1 plus 6 plus 1 plus 9 plus 9. 916199, and this comes out to be 120, and 120 mod 10 is 0. So you can see that the checksum bit is correct. So you can see from the examples that we have done so far, the last bit in all these are our check bit, which can be used for error detection. Now this code also can easily find out the transposition error. For example, if these 2 bits would have got exchanged, then what would have happened? Then here this would have been, these things would have changed, this would have become 9 and this would have become an 8. So this would have changed, this sum would have changed. So this earlier it was 9 times 3, 27, now it is 24, 3 less, and there is 1 more, so now 2 less. So this would have become 118, and this is not 0 modulo 10. So you can see this code can correct, can detect transposition error, and these are the most common error which happen when you are trying to read these barcodes. Okay. Now let us now move to some other applications. So we start with application of error control coding in CDs. You are familiar with the CD disk. It's basically a plastic disk of 120 in diameter, and it can be used for storing digital audio, video data. Now, the audio signal is sampled at 41.1 kilosamples per second, and it provides a listening bandwidth of 20 kilohertz. Each audio sample is sampled to quantized to one of the 256 levels, which provides a dynamic range of 96 dB and harmonic distortion of less than 0.005. Now, what are the sources of error in a CD disk? So, there could be small unwanted particles, dust particles, or there could be some air bubbles and things like that, which could have happened during manufacturing of these CDs, or fingerprint, scratches, dust particles from handling the CD. So, how does a CD corrects or these kinds of errors? You must have noticed, even if you have your CD has small scratches, but still your CD plays. So, how does it happen? This happens because of a very powerful error control coding which is used in the CDs. So, little bit of history. Basically, Philips and Sony were experimenting with this optical disc, and Philips engineers had a lot of problems controlling errors in the disc, and even if there would have been small scratches or dust particles, the whole data would essentially go away. So, whenever Philips were demonstrating the CD, they were very careful. They were just demonstrating with very, very clean CDs, and which did not have any scratches and things like that. And what Philips was actually doing was, they were trying a convolutional code to correct errors because of high coding gain provided by that. But the problem is, this storage channel is like an erasure channel. If there is scratch or something like that, there are neighboring bits which get affected and the data there is erased. So, convolutional codes are not good in correcting erasures, and that is why they were initially not successful. So, as I said, the problem was this storage media was a burst channel, and convolutional codes were not good in correcting burst error. So, there comes Reed-Solomon code, and so the CDs used basically a cross interleave Reed-Solomon codes, and there is 4 set of kind of hierarchy as far as error control and detection is concerned. So, there is an inherent forward error correction because of these Reed-Solomon code, but if the error burst exceeds the capability of the error correcting capability of the code, then the decoder also provides a level of erasure correction. So, there is a, in addition to error correction, there is also an erasure correction, and erasure is bunch of neighboring bits just getting erased, they are not being able to recover. So, the decoder has this capability. If the error correction fails, at second level the decoder can do erasure correction and try to recover those data. Third is, if the error burst exceeds the capability of erasure correction, then what it does, it tries to do some sort of an interpolation between reliable neighbors so as to interpolate what the data is. And if even interpolation fails, then basically the decoder just blanks out and you will hear like kind of a mute sound when the error is big enough that even the interpolation cannot work. So, a CD disk can correct error burst up to 4000 bits. So, try putting a scratch of 2.5 your CD will still work, I can guarantee that. It can detect error up to 12,000 bits, so it can detect errors of up to 7.5 long scratch. And of course, as I said, if the error burst exceeds the capability of erasure correction, then it tries to do interpolation to get back those bits. And undetected error happens very rarely, it happens every like 750 hours or so. So there's a very powerful error correcting codes which are used in CD. And interestingly, even these compact discs can withstand small punch holes in it. You can try putting a 8 mm hole into your CD and still it will be able to, correct the errors in the data, and the CD will still work. Now let's move to application for in satellite communication. So there is the standard digital video broadcasting S2 standard, which was one of the first standards to adopt low density parity check codes as their standard. So it's a de facto standard for high speed satellite communication, where typical throughput is less than 100 megabits per second. Now it uses as an outer code BCH code along with the inner LDPC codes, and it can support variety of block sizes. So it can support a block size of 16,200, and these are the various code rates that have been supported. So LDPC codes of rate. So these are the various code rates which are being supported by this standard. Similarly, for block size of 64,800, these are the various code rates that has been supported in this standard. Now there is another standard which is an upgradation of this DVB S2 standards called DVB S2X, which is an extended version of DVB S2 standard, and it allows more finer rates of LDPC codes. So you can see for the block length of 16,200, these were the rates which were supported by DVB S2. Now the DVB S2X can support further these rates. So it provides much finer code rate granularity compared to DVB S2 standard. And similarly for block size of 64,800, you can see these rates that you see here, from here, starting from here, these rates were not supported in DVB S2, which are supported in DVB S2X. What about deep space exploration? Now NASA again has specified as recommended standard. So these codes that you see here, these are have been prescribed for deep space communication, and this is for near earth communication. So it's for deep space communication, it supports 3 different block length, information block length 1024, 4096 and 16,384. So these 3 different information block lengths have been supported, and these are the various rates which have been supported. So correspondingly, these are the block sizes that you will get. Now for 10 gigabits Ethernet also, LDPC codes have been suggested. So LDPC codes have been used for forward error correction here for 10 gigabit Ethernet transmission over Ethernet, and it uses Reed-Solomon code based LDPC code. So the Reed-Solomon code is used to define the generator matrix of LDPC code, and this construction ensures that there is no cycle, 4 cycles in the LDPC code. Now let's move to applications in Wi-Fi. So IEEE 802.11n, which is a successor of IEEE 802.11ab and G, and it supports multiple antennas for transmission. So you could get about 150 Mbps in each data stream. If you use 4 antennas, you can get up to 600 Mbps. Now here 12 different LDPC codes have been suggested. Now use of LDPC codes in this standard is optional. The mandatory requirement is convolutional code, but they have specified LDPC codes which are optional, which can be used, and then these codes have been further reused in this standard 802.11ac to further increase the transmission rate. So I list here some of the block lengths which have been supported. So block lengths 648, and these are the various code rates supported here. Similarly, for block length of 1296, these are the various code rates which have been supported. Then we have IEEE 802.15, which is a standard for wireless personal area network. Here also there is a new file layer which is based on millimeter wave in 60 gigahertz band, which allows throughput up to 5 gigabits per second. Now here LDPC codes have been suggested. Now 5 different LDPC codes with 2 different block length has been suggested. Now typically the block size here is smaller, so as to ensure, and also this architecture is such that because we have to get 5 throughput up to 5 gigabits per second, so architecture is such that there is a lot of parallelism and the decoder can be implemented in parallel. So the rates which are supported, so block size 672, and these are the rate code rates which are supported here. Similarly, for block length of 1440, a code rate of 14 by 15 has been supported. Now another standard where LDPC codes have been used has been from very beginning is this WiMAX, and there are lots of codes which have been defined in this WiMAX standard. Again, use of LDPC code is optional here, but they have suggested lot of flexibility as far as block length is concerned, and 19 different block lengths have been considered and various different rates have been considered. Total of 114 LDPC codes have been defined or contained in this WiMAX standard. And as I said, here also the use of LDPC codes is optional. The mandatory requirement is convolutional code. And finally, I will conclude this discussion with IEEE 802.22 standard, which is basically for cognitive radio, opportunistic access over TV white spaces, the TV spectrum which is not being used for which can be opportunistically used for communication, and the whole idea of IEEE 802.22 is to provide rural connectivity. So here also they have specified lots of various LDPC codes, and in fact they have two new block lengths which were not there in WiMAX have been added, one corresponding to 384 bits, another corresponding to 480 bits. So this is another application where LDPC code is optional, convolutional code is mandatory, but LDPC code is optional, has been suggested. So this is not an exhaustive list of application. I just wanted to give you some flavor of where in practice we use linear block codes. Thank you.